Every autumn, the sky fills with travelers. 50 billion birds, lifting from their summer homes, turning toward warmth they have never seen but somehow already know. Welcome to the Sleepy Lab. Tonight, we drift through one of the oldest journeys on Earth, the migration of birds. We will follow them across oceans and mountain ranges, and into the quiet mystery of how they find their way home. If these slow journeys help you sleep, consider subscribing, one sleepy soul at a time. Now, let's begin. Every autumn, roughly 50 billion birds leave their breeding grounds. They move south, or toward the coast, or across open water, each species following a path shaped over millions of years. This is not a new event. Bird migration predates human civilization by tens of millions of years. Long before the first cities, before the first fires, birds were already crossing continents in the dark. It is one of the oldest recurring events in the natural world. And it happens quietly. Most of it happens at night, above sleeping towns, above dark fields, above the surface of the sea. Among all the travelers, one bird covers more distance than any other: the Arctic tern. Each year, this small seabird migrates from the Arctic to the Antarctic and back again, a round journey of roughly 70,000 kilometers. That is nearly twice the circumference of the Earth, completed in a single year, and then repeated the next year, and the year after that. Over a lifetime of about 30 years, an Arctic tern may travel a total distance equivalent to 3 round trips to the moon. 3 round trips to the moon and back in a body that weighs less than 100 grams. The tern does not rush. It rides the wind, follows the light, and arrives where it needs to be. But if the Arctic tern holds the record for total distance, another bird holds a different record entirely: the bar-tailed godwit. This shorebird, brown and unassuming, holds the record for the longest nonstop flight of any bird on Earth. Each autumn, it crosses the Pacific Ocean from Alaska to New Zealand without stopping once. The crossing takes about 11 days. The distance is roughly 11,000 kilometers of open water, with no land beneath it, no place to rest, no food, no fresh water. 11 days. During that entire crossing, the bar-tailed godwit does not eat. It does not drink. It does not sleep, not in any conventional sense. It simply flies. To make this possible, the godwit prepares its body in ways that seem almost impossible. In the weeks before departure, it eats almost constantly, storing fat beneath its skin and around its organs. By the time it is ready to leave, it has nearly doubled its body weight. A bird that might normally weigh around 300 grams departs at close to 600. But the body can only hold so much. To make room for all that fat, the godwit's digestive organs, the stomach, the intestines, actually shrink. They are not needed for the crossing, so the body reduces them, reclaims the space, and fills it with fuel instead. At the same time, the heart grows larger. The flight muscles grow larger. The body is rebuilding itself from the inside, becoming something optimized for a single sustained effort. And then it flies. By the time it reaches New Zealand, the godwit may weigh half what it did at departure. The fat is gone. The digestive organs will slowly rebuild. The heart and muscles will return to their normal size. The body will quietly undo what it did and begin preparing for the return. Migratory birds can lose up to half their body mass during a long non-stop flight. That number is worth sitting with for a moment. Half the body, consumed from within, converted into motion, into distance, into arrival. And yet, even during those 11 days over the Pacific, the godwit is not entirely without rest. Some migratory birds have developed a way of sleeping that does not require them to land or even to stop flying. It is called unihemispheric sleep. One half of the brain rests, the other half remains awake. One eye closes, the other stays open, watching the horizon, watching for danger, watching the stars. The bird sleeps and flies at the same time. Half dreaming, half alert, crossing an ocean in the dark. It is not the deep, still sleep you are drifting toward now. It is something thinner, something borrowed, just enough rest to keep going, taken in fragments, one hemisphere at a time. There is something very quiet about this image. A small brown bird, somewhere over the middle of the Pacific Ocean, in the middle of the night, flying south. No land in any direction. Stars above, dark water below. One eye open, one eye closed. It does not know the name of where it is going. It carries no map that we can see. And yet it is not lost, not even slightly. Something inside it knows the way. How it knows. That is where the story deepens, and that is where we will go next. But for now, let the godwit fly. Let it carry you a little further from the day, a little further from thought, out over the dark water, where the stars are very bright, and the wind is steady, and there is nothing to do but move, slowly, toward the south. The body knows how to rest, just as the godwit's body knows how to fly. One hemisphere at a time, if that is what it takes. There is another bird worth resting with for a moment. A hummingbird. The ruby-throated hummingbird weighs about 3 grams, roughly the same as a paperclip lying on a desk. You could hold one in your closed hand and barely feel it. And yet, each autumn, this small creature crosses the Gulf of Mexico in a single nonstop flight, roughly 800 kilometers of open water. No land, no rest, no shelter from the wind. 800 kilometers for something that weighs 3 grams. It does not stop. It cannot stop. There is nowhere to land. So it simply continues, beating its wings somewhere between 50 and 80 times per second, hour after hour, through the night and into the following day, until the far shore finally appears. We do not fully understand how it manages this. Physics alone seem improbable, and yet the hummingbird has been making this crossing for a very long time, long before we were here to find it improbable. There is a warbler, too. The blackpoll warbler. It weighs about 12 grams, 4 paperclips, perhaps. Each autumn it gathers itself on the northeastern coast of North America, waits for the right wind, and then launches itself out over the Atlantic Ocean. It will fly for up to 3 days without rest, without food, without landing, until it reaches the coast of South America far below. 3 days. Over open ocean, in a body the size of a large grape. The blackpoll warbler does not look like a long-distance athlete. It looks like a small, quiet bird sitting in a bush. But inside that small body, in the weeks before departure, something extraordinary has been happening. Fat has been accumulating. Organs have been shifting. The body has been preparing itself, quietly and precisely, for something it has never done before, and yet somehow already knows how to do. Let that settle for a moment. A body preparing itself for a journey it has never taken, guided by instructions it was born carrying. Now consider altitude. Some shorebirds migrate at heights above 6,000 meters. The air up there is thin and bitterly cold. Temperatures well below freezing. Oxygen levels that would leave a human gasping and confused within minutes. And yet birds pass through this space in sustained, powerful flight, hour after hour, as though the cold and the thinness of the air were simply the conditions of the world, nothing more. Bar-headed geese go even higher. They have been recorded crossing the Himalayas at altitudes above 7,000 meters, higher than most of the peaks below them, in air so thin that the oxygen available is less than half what it is at sea level. They do not slow down. They do not struggle, at least not in any way we can easily observe from below. They simply cross. Part of the reason is in their blood. Bar-headed geese carry a form of hemoglobin, the molecule that ferries oxygen through the bloodstream, that is slightly different from the hemoglobin of lowland birds. This difference allows it to bind oxygen more efficiently at low atmospheric pressure. A small molecular adjustment, written into the genome over generations of high-altitude flight, that makes the impossible merely difficult. The body, again, preparing itself for what it needs to do, not through thought or decision, but through the slow, patient work of inheritance. And then there is the swift. The common swift spends most of its life in the air. It lands only to breed. Everything else, feeding, sleeping, even mating, happens on the wing. Over a lifetime, a swift may fly 2 million kilometers. 2 million. That is roughly 5 trips to the moon and back, traveled entirely through the air of this one small planet, in a body no larger than your fist. The swift does not migrate in the way we have been describing. It does not travel between a breeding ground and a wintering ground in the conventional sense. It simply keeps moving, following the insects, following the warmth, tracing great arcs across the sky of 2 continents. It is always somewhere. It is never quite anywhere for long. There is something restful in that image, if you let it be. A bird that has made peace with motion, that does not need to arrive. And then, at the other end of the scale, there is the albatross. The wandering albatross has a wingspan of up to 3.5 meters, the largest of any living bird. When it spreads its wings, it spans a distance wider than most doorways are tall, and it uses those wings in a way that is almost unlike flying as we usually think of it. Albatrosses practice something called dynamic soaring. They extract energy from the difference in wind speed between the surface of the ocean and the air a few meters above it. They rise into the faster wind, bank, descend into the slower wind near the waves, and use the difference in speed to propel themselves forward, almost without effort, almost without a single wing beat. They can travel hundreds of kilometers in a day while expending very little energy at all. Some albatrosses circumnavigate the Southern Ocean multiple times in a single year, tens of thousands of kilometers, in great looping circuits around the bottom of the world, riding the wind as though the wind were a road laid out specifically for them. In a sense, it is. The wind patterns of the Southern Ocean have been there for millions of years. The albatross has been there, in one form or another, for millions of years. The bird and the wind have shaped each other, slowly, across deep time. Which brings us to something worth holding gently as you drift. Migration routes are not random. They are not improvised each year by birds making their best guesses. They are ancient corridors, shaped over millions of years by geography, by the reliable patterns of wind, by the locations of food and water and safe resting places. They are, in a sense, written into the landscape itself and written into the birds that travel them. There are names for some of these corridors. The East Atlantic Flyway, which carries birds along the western edge of Europe and Africa. The Mississippi Flyway, which funnels the birds of a continent down through the heart of North America. The East Asian Australasian Flyway, which connects the breeding grounds of the Arctic with the coasts and wetlands of Southeast Asia and Australia. These are not lines on a map. They are living rivers of movement, billions of individual journeys, each one slightly different, all of them following the same deep grain of the world. A grain laid down long before any map existed, long before anyone was watching. The birds do not know the names of these flyways. They do not need to. They carry something older than names, a sense of direction, a sense of distance, a pull toward a place they may never have been, encoded in the very structure of their cells. And somewhere along each of these ancient corridors, right now, tonight, birds are moving. Over dark water, over sleeping cities, over mountain ranges where the air is thin and cold, and the stars are very close. Each one carrying its invisible map. Each one going exactly where it needs to go. Along the East Asian Australasian Flyway, roughly 50 million waterbirds move each year. 50 million godwits and sandpipers, knots and curlews, each one following the same invisible thread southward through the sky. From the Arctic tundra, where they were born, down through the coasts of China and Korea, through the islands of Southeast Asia, all the way to the mudflats and estuaries of Australia and New Zealand. A river of wings so vast, it is difficult to hold in the mind all at once. And yet each bird within it is alone in a certain sense. each one navigating by its own instruments, reading its own version of the world. There are places along these ancient corridors where the land itself gathers the birds together, narrow passages, bottlenecks where geography leaves no other choice. The Strait of Gibraltar, where Europe and Africa nearly touch across a thin seam of water. On the right day in autumn, the sky above that strait fills with birds of prey, eagles and harriers and honey buzzards, all funneled to this one crossing point because the open sea beyond is too wide, and the land here is as close as it will ever get. Panama is another such place, a slender bridge of land connecting two continents, and every migrating bird that travels between them must pass over it. The skies above Panama in October hold some of the most concentrated streams of migration anywhere on Earth. And then there is Hawk Mountain in Pennsylvania, a single ridge in the Appalachians, running in just the right direction, catching the updrafts that rise along its western face. On peak autumn mornings, thousands of raptors pass that ridge, broad-winged hawks in their hundreds, then their thousands, tilting on the warm air, circling upward in loose spirals before gliding south. Ospreys, sharp-shinned hawks, golden eagles, moving with a slow and unhurried gravity. All of them following the ridge, all of them reading something in the air and the light that tells them, this way, south, keep going. But what exactly are they reading? This is one of the deepest questions in all of biology, and the answer, as far as we can tell, is not one thing. It is several things at once. Migratory birds navigate using at least 4 distinct systems: the sun, the stars, the magnetic field of the Earth, and the landmarks of the physical world, coastlines, rivers, mountain ranges, the shapes of things remembered. No single system is sufficient on its own. Together, they form something more reliable than any one of them could be alone. The sun compass is perhaps the most intuitive to understand. A bird can determine direction by tracking where the sun sits in the sky, but only if it knows what time it is. Because the sun moves, it rises in the east, arcs overhead, sets in the west. Its position alone tells you nothing unless you know the hour. Birds know the hour. Somewhere deep in their biology, there is a clock, a circadian rhythm, precise and self-sustaining, that runs continuously through the day and night. By comparing the sun's current position against the time their internal clock is keeping, a bird can calculate which direction is south, which is north, which is the way it needs to go. It is a form of celestial navigation that human sailors took centuries to develop. Birds are born with the capacity for it. But the sun disappears. Clouds gather. Overcast days arrive, and the sky becomes a uniform gray, with no shadow, no arc, no visible source of light. On those days, many birds switch to a different instrument entirely: the magnetic compass. The Earth is wrapped in a magnetic field, invisible, pervasive, extending from deep within the planet's core out into the space above the atmosphere. We cannot feel it, but birds, it seems, can read it. What they detect is not the direction of the field in the way a compass needle points. It is something subtler than that: the inclination, the angle at which the field lines dip into the surface of the Earth. Near the poles, the field lines plunge steeply downward. Near the equator, they run nearly parallel to the ground. A bird sensitive to this angle can distinguish equatorward from poleward, can feel, in some sense, whether it is moving toward the warmth of lower latitudes or back toward the cold of the high north. This is a compass that works even in total darkness, even underground, in principle. It does not require light or landmarks or any external reference at all. It is always there, always pointing, always available. But how does a bird actually sense it? This is where the science becomes genuinely strange and genuinely beautiful. In the retinas of migratory birds, there is a protein called cryptochrome. It is found in many living things, in plants, in insects, in the cells of our own bodies, where it plays a role in regulating circadian rhythms. But in the eyes of migratory birds, it appears to do something else as well. When light strikes cryptochrome, it triggers a chemical reaction. The reaction produces pairs of molecules, called radical pairs, in which the electrons are quantum mechanically entangled, and these paired molecules are sensitive to magnetic fields. The presence of a magnetic field changes the way the reaction proceeds, altering the ratio of products it produces. The current hypothesis, and it remains a hypothesis, carefully held, is that this chemical difference creates a faint signal, a signal that the bird's visual system can detect, which would mean something remarkable. It would mean that birds do not feel the magnetic field the way we feel warmth or pressure. They may see it, or something like seeing a subtle overlay on their visual field, a faint pattern or gradient that shifts as they turn, that brightens or dims depending on which way they are facing. The magnetic field of the Earth, rendered as something like light. There is evidence for this. Researchers studying European robins found that when they covered the bird's right eye, its ability to orient magnetically was disrupted. Cover the left eye, and the bird could still navigate. The effect was asymmetric, tied to one eye, one side of the brain. This is not what you would expect from a mechanical sensor, like iron particles responding to a field. It is what you might expect from a visual process, something happening in the retina, processed by the visual cortex, perceived as a kind of image. The robin, sitting quietly in the dark before its first migration, may be looking at the magnetic field of the Earth the way we look at the glow of a distant light. Soft, directional, telling it something about where it is and where it needs to go. We do not know this for certain. The science is still unfolding, still debated, still full of open questions, but the evidence points in this direction, gently and persistently. A small bird, weighing almost nothing, carrying in its eye a molecule that responds to the invisible geometry of the planet. Reading the field of the Earth the way you might read the quality of light through a window, not thinking about it, not calculating, simply knowing. South is that way. The night is long, and the ocean is wide, and the stars are turning slowly overhead. And the bird flies on. There is something else worth noting about the robin's eye. The right eye, specifically, in experiments where researchers covered one eye or the other, it was the right eye that mattered. Cover the left, and the robin still orients correctly. Cover the right, and something is lost. The compass falters. The bird becomes uncertain. This asymmetry is not fully explained, but it suggests the magnetic sense is not simply distributed evenly across both eyes. The way ordinary vision is, it is lateralized, weighted toward one side, the way language is weighted toward one hemisphere in the human brain. A quiet reminder that even the most ancient biological systems carry their own particular architecture. And the cryptochrome molecule itself, the one thought to carry this magnetic sensitivity, is delicate in ways that are still being mapped. Certain radio frequencies, very weak electromagnetic fields, far too faint to feel, can disrupt the chemical reaction that cryptochrome undergoes. In laboratory settings, birds exposed to these frequencies lose their magnetic orientation. They become, in a precise and measurable way, lost, not distressed, not visibly changed, simply no longer pointing in the right direction. This is one of the stranger findings in the field, that a signal too faint for any human instrument to detect as meaningful could quietly erase a bird's sense of where south is. It suggests the cryptochrome reaction operates at a threshold of sensitivity that is almost difficult to hold in mind. For a long time, the magnetic sensor was thought to be something else entirely. Small deposits of iron-containing minerals were found in the beaks of some birds, magnetite, the same mineral that gives lodestones their pull. It seemed a natural candidate. Iron responds to magnetic fields. The beak is close to the brain. The hypothesis was tidy and appealing. For years, it was the leading explanation. More recent work has complicated that picture. The iron deposits in bird beaks appear, on closer examination, to be associated with cells of the immune system rather than with nerve cells connected to the brain. They may have nothing to do with navigation at all. They may simply be iron stored in a particular tissue, for reasons unrelated to the compass. This is how science often moves, not in straight lines, but in revisions. A promising structure turns out to be something else. The question reopens. The search continues. And so the question of how birds sense magnetic fields remains, as of now, genuinely open. The cryptochrome hypothesis is the most supported, but it is not settled. The full picture has not yet come into focus. This is not a failure of the science. It is simply where the science currently stands, at the edge of something it can almost see, but not quite. One of the most active areas in all of sensory biology. Quietly, persistently unresolved. Now consider the young bird. It has never made this journey before. It has no map drawn by experience, no memory of a route flown in a previous year. And yet, when the season turns and the restlessness rises in its body, it knows, in some sense of the word, which way to go. What it carries is not a map. It is something more like a program, a direction, and a duration. Fly roughly southwest for approximately this many days. That is the inherited instruction, encoded not in memory but in the genome itself. Researchers sometimes call this vector navigation, a vector being, in the mathematical sense, a direction combined with a magnitude. The young bird holds a direction and flies it for a set amount of time, and if all goes well, it arrives somewhere close to where its species has always wintered. The evidence for this comes from displacement experiments. Young birds, caught during their first autumn migration and moved hundreds of kilometers off course, do not correct back toward their birthplace. They correct toward their genetically programmed destination. They resume flying in the inherited direction, as if the displacement had not happened, as if the only instruction they carry is, go there, not, go back to where you started. This is a subtle but important distinction. The young bird is not navigating in the full sense of the word. It is executing a program, a very old program, refined over countless generations, reliable enough to get most birds close enough to survive. But it is not the same as what an adult bird does. An adult bird that has made the journey before carries something more. It has learned the actual geography, the shape of coastlines, the position of mountain ranges, the smell of particular places, the way the stars look from a specific latitude. It can navigate back to a known location from an unfamiliar starting point, not just fly in a direction, but find a place. This is sometimes called true navigation, to distinguish it from the vector system of the young bird. True navigation requires two things: knowing where you want to go and knowing where you currently are. Like reading coordinates on a map, you need both pieces of information, or the map is useless. The young bird has the destination encoded, but it does not know where it is in any flexible sense. It only knows to keep going in the inherited direction. The adult has both. How the adult determines its current position, how it reads its own coordinates from the landscape and the sky, is still not fully understood. This is one of the deeper unsolved questions in migration biology. The sun, the stars, the magnetic field, all of these provide directional information. But direction alone does not tell you where you are. You need something more. Some sense of position, of displacement, of how far you have drifted from where you expect it to be. The answer may involve multiple cues working together in ways that are difficult to disentangle. And for some species, it may involve something that seems, at first, unlikely: scent. For certain birds, particularly seabirds that spend their lives over open ocean, the sense of smell may contribute to navigation in ways that are only beginning to be understood. The ocean does not look the same from every direction, but it may smell different. Different water masses carry different chemical signatures, shaped by the life within them, by the currents that move them, by the land they have passed near. Experiments with shearwaters, seabirds that range across vast stretches of open water, showed that when their sense of smell was blocked, their ability to find their way home was impaired, not eliminated, but measurably reduced. They could still orient, but something was missing from their navigation. The implication is that scent is not merely incidental to these birds. It is part of the toolkit, part of the map. A map built not from lines on paper, but from the invisible chemistry of the world. the smell of a particular stretch of ocean, the faint trace of a coastline carried on the wind, the chemical memory of a place visited years before. The adult shearwater, crossing thousands of kilometers of open water, may be reading the ocean the way a person reads a familiar landscape, not consciously, not deliberately, but with a deep and practiced recognition. This is where you are. This is the way home. And pigeons have offered a similar kind of evidence. Studies of pigeons raised near sites where the wind patterns were artificially disrupted, where the normal flow of air across the landscape had been altered, showed that these birds developed different homing routes than pigeons raised nearby in undisturbed air. Not wrong routes, exactly, but different ones. As if the map they'd built was drawn from different information. The suggestion is that birds may construct a kind of olfactory atlas of their home region, a map assembled over time from the scents arriving on winds from different directions. A smell from the north, a smell from the east, each one associated with a bearing, a direction, a place. This idea, the olfactory map hypothesis, remains debated among researchers. Not all experiments have supported it. Not all species seem to rely on it equally, and the mechanism by which a bird would translate a scent into a compass bearing is still not clearly understood. But the evidence is persistent enough that it cannot be set aside. The world, it seems, is legible in more ways than we tend to assume, readable not only through light and magnetism, but through the slow, invisible language of scent carried on moving air. And yet, for many birds, the most important map of all is written in the sky. Many of the world's songbirds migrate at night. This may seem counterintuitive. Night is when predators hunt. Night is when visibility is low. And yet, for small birds crossing open country, darkness offers something value in a half and a stillness in the air that makes flight more efficient. Above a sleeping landscape, a warbler weighing 12 grams lifts into the dark and begins to move. It is not flying blind. It is reading the stars. The stellar compass works differently from the magnetic one. It is not inherited in the same way. It is learned, and the learning happens early, in a window of time before the first migration, when the young bird is still close to where it hatched. During this period, the bird watches the night sky. Not casually, not incidentally. It watches with something that functions like attention, tracking the slow rotation of the stars around a single still point. That point is the celestial pole. In the northern hemisphere, the stars appear to wheel around a fixed center, and near that center sits Polaris, the North Star, almost motionless, while everything else turns. The young bird learns this. It learns which part of the sky stays still, and it learns that still point is north. This is the anchor of the stellar compass, not any single star, but the axis of rotation itself. Researchers demonstrated this with a quiet and elegant series of experiments. Young birds were placed inside planetariums, domed rooms where an artificial sky could be projected overhead. Some birds were shown a sky that rotated around a different star, a false pole placed elsewhere in the dome. When these birds were later tested for orientation, they pointed toward that false pole. They had learned the wrong north and trusted it completely. The stellar compass, it turns out, is not hardwired. It is written during a sensitive period by the sky itself into the young bird's memory. Whatever the sky teaches in those early weeks becomes the reference for everything that follows. There is something quietly remarkable in this, that a bird's sense of direction is not simply given to it, but earned through weeks of patient watching. The sky as teacher, the turning stars as the first lesson, and then, as the season shifts, something else begins. A caged bird, kept indoors, with no view of the sky and no change in temperature, begins to grow restless at night. It hops, it flutters, it orients itself repeatedly in one direction, pressing against the side of the cage that faces the way it would fly if it were free. This state has a name. In German, it is called Zugunruhe, migration restlessness. The word carries a kind of weight. zog, meaning pull or migration, unru, meaning unrest. It is one of the most evocative words in the study of animal behavior. The bird is not responding to the stars. It cannot see them. It is not responding to landmarks or wind or the smell of distant places. It is responding to something internal, a signal arising from within its own body, telling it that it is time. And the signal is remarkably precise. Birds that would normally migrate long distances show more intense zugonru than birds that migrate short distances. The restlessness scales with the journey, as if the body already knows how far it needs to go and is already measuring out the effort. The trigger for all of this is light. Not warmth, not temperature, at least not primarily. Light? As the days grow longer in spring, the changing ratio of light to darkness is detected by photoreceptors, not only in the eyes, but in the brain itself, where light filtering through the thin bones of the skull can reach specialized cells sensitive to its presence. This is one of the stranger facts in bird biology, that light can penetrate the skull and be detected by the brain directly, bypassing the eyes entirely. The signal passes to the pineal gland and to the hypothalamus, two small structures deep in the brain that serve as the body's master timekeepers. There, the changing day length is translated into hormones, and the hormones begin to change everything. Fat accumulates beneath the skin and around the organs. The liver enlarges slightly, working to convert food into the fatty acids that will fuel the journey. The testes or ovaries grow in preparation for the breeding season that waits at the end of the migration. The bird's body is being remade from the inside. All of this set in motion by the lengthening of the day, by the slow, incremental addition of minutes of light as the earth tilts toward the sun. A few more minutes of light each morning. And somewhere inside a small bird sitting on a branch, a clock begins to run. In autumn, the process reverses. The days shorten, the light diminishes, the hormonal tide turns in the other direction, and the pull toward the south begins. Zuganrua returns, but now oriented differently, toward warmer latitudes, toward the wintering grounds, toward the place the bird has never been but somehow already knows to seek. The inherited program activates a direction, a duration, a distance encoded not in memory, but in the structure of the nervous system itself, passed down through generations of birds that survived by moving and perished by staying. All of this, the star watching, the restlessness, the hormonal cascade, the fattening body, is preparation for something the bird has not yet done, but is already, in some deep sense, ready for. The night will come, the stars will appear, and the bird will lift from its branch and begin. And so the bird lifts, not because it decided to, in any way we would recognize as decision, but because the light has been diminishing evening by evening, and something ancient inside it has been counting. The southward pole is not a thought, it is a tide. In most species across the northern hemisphere, the shortening of autumn days is the signal that sets everything in motion. The same signal, arriving the same way it has arrived for millions of years, received by photoreceptors buried deep in the brain, translated into hormones, translated into restlessness, translated into flight. The bird does not know why it goes south. It only goes. Near the equator, the days barely change at all. The sun rises and sets at nearly the same hour throughout the year. And so the light-based clock that governs so much of migration becomes unreliable there. Some species living close to the equatorial belt have found other signals to read. The arrival of the rains, the sudden flush of insects that follows a wet season, the ripening of fruit in a forest that was bare the month before. The world offers many kinds of calendars. Birds have learned to read more than one. But for the billions of birds that breed in temperate and Arctic latitudes, the shortening day remains the primary clock. And that clock, for now, still runs, though the world around it is changing. Over recent decades, something has shifted in the timing of migration, measurably, across many species. in ways that researchers have been able to document through long records of first arrivals, first eggs, first songs heard in spring. Some species are arriving at their breeding grounds earlier than they did 50 years ago. The springs are warming. The insects are emerging sooner, and some birds, particularly short-distance migrants that winter not far from their breeding grounds, have adjusted, arriving a few days earlier, tracking the shift in the season with something close to precision. But others have not adjusted, or have not adjusted enough. Long-distance migrants face a particular difficulty. They depart from wintering grounds thousands of kilometers away, guided by the lengthening of days at a latitude far from where the change is actually happening. The signal they receive tells them what the season was like, historically, at their destination. It does not tell them what the season is like this year. And so they arrive on schedule, their inherited schedule, to find that the world has moved on without them. The timing of a breeding bird's arrival is not arbitrary. It is calibrated, over generations, to coincide with a narrow window, the peak of insect abundance, which itself tracks the emergence of leaves, which itself tracks the warming of the soil, which itself tracks the temperature of the air. Each link in this chain depends on the one before it. Temperature rises, plants flower and leaf out, insects hatch and multiply. Birds arrive to feed their young on the insects at the moment of greatest abundance. This chain of dependencies, temperature, plants, insects, birds, is sometimes called a phenological cascade. Each element is timed to the others, and when one element shifts faster than the rest, the cascade begins to fall out of step. A warbler arrives on the day its ancestors always arrived, but the caterpillars it needs to feed its nestlings have already peaked and declined. The window is past. The chicks hatch into a forest that is, in terms of food, already past its moment. This is called a phenological mismatch, and it is quiet. There is no visible catastrophe. The forest still stands. The bird still sings. But fewer young survive. And over years, over decades, the population slowly thins. Some species can adjust. Short-distance migrants, wintering in climates that warm, along with their breeding grounds, receive earlier cues and can depart earlier. They track the shift, imperfectly but adequately. Long-distance migrants cannot do this as easily. They are too far away. The signal they receive is the wrong signal for the world they are returning to. And so, across the world, long-distance migrants are declining faster than short-distance migrants. Not everywhere, not in every species, but the pattern is there in the data, a quiet statistical divergence between those that can adjust and those that cannot. The wood thrush is one of the birds that cannot. It winters in Central America and breeds in the forests of eastern North America, filling those forests each spring with a song that carries through the trees like something poured from a vessel, clear, liquid, unhurried. Since the 1960s, its population has declined by roughly 60%. 60%. More than half of all the wood thrushes that once sang in those forests are simply gone. Climate mismatch is one part of the story, but only one part? A bird crossing an ocean, navigating by stars and magnetic fields, carrying within it a route encoded over millions of years. All of that is extraordinary. And yet the journey is only as good as the places it passes through. Migration is not a single flight. It is a chain of flights, connected by stops, places where birds land, rest, and eat, places where they rebuild the fat reserves that the previous leg of the journey consumed. Without these stopover sites, the chain breaks. A stopover site is not simply a convenient field or a pleasant stretch of coastline. For many species, it is a specific place, a place their ancestors used, a place with the right food at the right time, a place that may be irreplaceable because nothing else nearby offers what it offers. Lose a stopover site, and you do not lose one bird. You lose a link in the chain that millions of birds depend on. Along the coast of the Yellow Sea, between China and the Korean Peninsula, there are, or were, vast tidal flats, shallow, muddy, extraordinarily rich in the small invertebrates that shorebirds need to fuel the final legs of their northward journeys. For millions of shorebirds flying the East Asian Australasian flyway, these flats were not optional. They were essential. The birds arrived lean from the south, fed intensively for days or weeks, and departed fat enough to reach their Arctic breeding grounds. Over recent decades, much of this coastline has been reclaimed, drained, filled, converted to land for industry and agriculture. The tidal flats have shrunk dramatically, and the birds that depended on them have shrunk with them. Some shorebird populations that relied on yellow sea stopovers have declined by more than 70%. Species that were common within living memory are now rare. The flats that remain are crowded with birds that once had far more space, far more food, far more time. The birds still come. They still follow the ancient route, the inherited direction, the pull of the season. They arrive at the coast and find less than their ancestors found. They feed on what remains and depart carrying less than they need. Some make it, some do not. The routes taken by migratory birds are not just paths across a map. They are relationships between a bird and a coastline, between a warbler and a forest, between a shorebird and a mudflat that has been accumulating invertebrates since long before any human walked beside it. When those relationships are broken, the birds do not simply find another way. They carry the old way inside them, written in their genes, encoded in their restlessness, pointing toward a place that may no longer be what it was. And still they go. There is another kind of loss that happens not in the daylight, not over mudflats or coastlines, but in the dark above our cities. Migratory songbirds travel mostly at night. They lift off after sunset, when the air is cooler and calmer, when the stars are visible and the magnetic field is undisturbed. For millions of years, the night sky above them was dark. The only lights were the stars they navigated by and the faint glow of the moon moving through its phases. Then, gradually, the ground began to glow. Cities produce light that rises upward into the sky, a diffuse, orange warmth that spreads for kilometers in every direction. To a small bird flying at altitude, this glow is deeply confusing. The systems that evolved to read starlight and magnetic inclination were not built for this. A bird drawn toward a city's brightness can circle for hours, unable to orient, burning energy it cannot spare. Millions of birds die this way each year. They collide with illuminated buildings, with glass towers that reflect the sky, with windows that show a bird the image of a tree it will never reach. The glass does not announce itself. It simply returns the world, and the bird flies into the reflection of the world it was trying to reach. In North America alone, an estimated 1 billion birds die from window collisions every year. Many of them are migrants, birds that crossed hundreds or thousands of kilometers of open water and forest, only to meet an invisible surface in the final moments of a night flight. 1 billion is a number that resists comprehension. It is easier to hold a single bird, a warbler, perhaps, weighing 12 grams, its feathers still carrying the faint chemical signature of the forest where it was born. It crossed the Gulf of Mexico in the dark. It navigated by stars and magnetic fields, and something we do not yet fully understand. It arrived at the coast just before dawn, exhausted, and began to look for food in the trees near a city. And then the lights came on. The solution, where it has been tried, is simple. Turning off or dimming building lights during peak migration periods reduces collisions significantly. The birds, freed from the pull of artificial brightness, continue on their way. The intervention costs almost nothing. The benefit, measured in lives, is large. But to know when to dim the lights, you need to know when the birds are flying. This is where the radar comes in. Weather radar networks were built to track rain and snow, to watch moisture moving through the atmosphere and warn of storms. They were not designed with birds in mind, but birds, flying in their millions, are large enough to return a signal. And for decades, meteorologists noticed strange blooms appearing on their screens on clear autumn nights, echoes that spread outward from the landscape like a slow pulse. then faded toward dawn. Those blooms were birds. Researchers began to study these echoes carefully. They found that the radar could reveal not just that birds were flying, but how many, in what direction, at what altitude, and across what area. On peak migration nights, the screens show something almost like a tide, a wave of living movement spreading across an entire continent in the hours after sunset. The scale of what the radar revealed was difficult to absorb. Hundreds of millions of birds moving in a single night, corridors of flight following river valleys and coastlines, pulses of migration that could be predicted, to some degree, from the weather, a cold front passing, a shift in wind direction, and suddenly the sky above a sleeping city is full of birds that no one on the ground can see or hear. Researchers have used this data to map migration intensity across entire continents, watching the season unfold in near real time. The patterns that emerge are both ancient and newly visible, routes that birds have followed for thousands of years, now rendered as light on a screen. A project called Birdcast has taken this further, combining radar data with machine learning to forecast migration intensity the way a weather service forecasts rain. On nights when the models predict heavy migration, alerts go out to cities asking building managers to dim their lights. Some cities have responded. The birds that fly over those darkened towers continue south, unaware of the intervention, carrying their inherited directions toward destinations they have never seen. Radar shows the movement of populations, but to follow a single bird, to know where one individual goes, what route it takes, where it stops, how long it rests, requires something smaller and more personal. Satellite tracking has made this possible. A tiny transmitter, attached to a bird's back like a small rucksack, sends its position to satellites overhead. The data comes back as a line on a map, a thread of coordinates stretching across continents, across oceans, across seasons. A cuckoo named Anan was fitted with such a transmitter in Mongolia. Researchers watched as he flew south and west, crossing mountain ranges and deserts, crossing the Arabian Peninsula, crossing the Indian Ocean, arriving eventually in sub-Saharan Africa. Then, months later, the signal began to move again, northward, retracing something close to the outbound route, back across the ocean, back across the desert, back to Mongolia. The total journey was more than 20,000 kilometers. One bird, one line on a map. And yet that line contains within it everything: the timing of departures, the choice of altitudes, the selection of stopover sites, the response to weather, the pull of the breeding ground in spring. For smaller birds, even a satellite transmitter is too heavy. A device that weighs a gram is a significant burden to a warbler that weighs 12. So researchers developed geolocators, instruments so small they weigh less than half a gram, light enough to attach to a songbird without meaningfully affecting its flight. Geolocators do not transmit, they simply record. They measure light levels continuously, logging the precise moment of sunrise and sunset each day. When the bird is recaptured, which requires finding the same individual again, months or years later, which is itself a small miracle, the data is downloaded and analyzed. From the timing of sunrise and sunset, it is possible to calculate latitude and longitude. Roughly, the precision is limited. A position might be accurate to within a few hundred kilometers, but for routes that were previously entirely unknown, even an approximate line across a map is a revelation. These small devices have shown that some species take completely different routes in spring and autumn, looping across the hemisphere to exploit different winds. They have shown that birds wintering in places no one suspected. They have shown that the routes encoded in a bird's genes are more varied, more flexible, and more ancient than anyone had imagined. A warbler weighing less than a handful of seeds, carrying a device lighter than a raindrop, crossing an ocean in darkness, and somewhere in its small brain, a map that no human drew, pointing toward a place it has never been but somehow already knows. The technology that follows these birds is new. The knowledge the birds carry is not, and yet the routes themselves hold their own kind of story. Loop migration is the name given to a pattern that surprised researchers when geolocator data first made it visible. A bird does not simply retrace its path. It goes out one way and returns another, tracing an ellipse across the hemisphere rather than a straight line back and forth. The outbound journey follows one arc. The return follows a different one entirely. The loops are not accidents. They are solutions, shaped over generations to match the rhythms of wind and weather. A route that carries favorable tailwinds in autumn may face headwinds in spring. So the bird takes a different road home, one that the winds of that season prefer. The planet's great circulation of air, its belts of trade, winds and westerlies, its seasonal reversals. All of this is written into the shape of a migration route, if you know how to read it. Some loops span entire ocean basins. Others are subtler, a few hundred kilometers of difference between the outbound and return path. But in each case, the bird is not wandering. It is following a course refined across thousands of generations, adjusted and readjusted until the geometry of the journey matched the geometry of the world. Consider the northern wheatear. It is a small bird, slight and quick, that breeds across the entire sweep of the Arctic, from Alaska in the west, across Canada, across Greenland, across Siberia, all the way to the far eastern edge of the continent. In autumn, all of these birds travel to the same place, sub-Saharan Africa. The wintering grounds are shared, but the routes to reach them are not. The Alaskan wheatears face a particular challenge. Africa lies to the east and south, but the shortest path across the Atlantic is not the path they take. Instead, they fly west, across the Bering Sea, across Siberia, across Central Asia and the Middle East. A journey of roughly 15,000 kilometers, curving the long way around the world to reach a destination that, as the crow flies, is far closer in the other direction. Why? The answer lies in history. The wheatear's ancestors did not begin in Alaska. They began somewhere in the Old World, in Europe or Asia, and expanded their range eastward over thousands of years, following the retreating ice, colonizing new breeding grounds as the Arctic opened up. Alaska was the last frontier, reached after the range had already stretched across an entire continent. And when autumn came, those Alaskan birds did what their ancestors had always done. They flew back the way they came, west, toward the ancestral wintering grounds. The route was already encoded. The destination was already known. Only the starting point had changed. Migration routes, in this sense, are evolutionary fossils. They preserve the memory of journeys made long ago, by ancestors in different places, under different conditions. The route a bird flies today may reflect a range expansion that happened 10,000 years ago, or 100,000. The ice ages compressed and redirected these ancient paths. The warming that followed stretched them outward again. And through all of it, the routes persisted, not written in stone, but written in genes, passed from parent to offspring, adjusted at the margins, but faithful at the core. This is why the same species can carry entirely different routes in different populations. Geographic isolation, over enough generations, allows each group to accumulate its own inherited direction, its own timing, its own arc across the map. The routes diverge the way languages diverge, slowly, through accumulated small differences, until two populations that once shared a common path are flying in opposite directions. The black-capped warbler offers one of the most striking examples of this. For most of its history, the Central European blackcap migrated southwest in autumn, crossing the Mediterranean and the Sahara to winter in West Africa. That was the route. It was ancient and reliable and well-established. Then, sometime in the middle of the 20th century, something shifted. A small number of blackcaps began flying northwest instead of southwest. They crossed the English Channel. They wintered in Britain. The first records appeared in the 1960s, a handful of birds, unusual enough to attract attention. But the numbers grew. Decade by decade, the northwest wintering population increased, quietly and steadily, until it became a recognized and substantial part of the species' range. Genetic studies revealed what was happening. The tendency to fly northwest rather than southwest was heritable. It was encoded in the bird's genes, not learned from experience or copied from neighbors. The birds carrying this tendency survived the British winter, milder than it once was. and supplemented by garden feeders left out by people who welcomed the unexpected visitors. They returned to breed in spring. They passed the tendency to their offspring, and the offspring passed it on again. Over roughly 60 years, a new migration route established itself within a single species, not through the slow grinding of geological time, but within the span of a human lifetime. It is one of the clearest documented examples of rapid evolutionary change in a migration route, a window into the process by which ancient routes were first created, playing out in near real time. What it shows is that migration is not fixed. It is not a rigid program running unchanged since the Pleistocene. It is a living strategy, responsive to selection, capable of shifting when conditions change. The routes that seem so ancient and inevitable are themselves the products of change, of populations that once flew shorter distances and gradually flew farther, of ancestors that once wintered nearby and slowly pushed their wintering grounds south and south and south until they were crossing oceans. The evolution of migration is thought to have begun simply: a population of birds that moved a short distance to exploit a seasonal surplus of food. Insects emerging in spring, fruit ripening in autumn, survived better than those that stayed. The movement was modest at first, a few hundred kilometers, perhaps, enough to reach a richer patch of habitat before the season closed. But modest movements, if they improved survival and breeding success, were favored. And over generations, the movements lengthened. Each increment that brought a bird to better food, or away from a harsher winter, or to a breeding ground with fewer competitors. Each increment was tested against the alternative of staying put, and if it won, it spread. The costs were real. The energy, the danger, the risk of storms and predators, and disorientation over open water. But the benefits, generation after generation, outweighed them. And so, the distances grew. What began as a short seasonal shift became a continental crossing. What began as a continental crossing became an ocean passage. What began as an ocean passage became, in the case of the Arctic tern, a journey from one pole to the other and back again, year after year, for a lifetime. All of this, the loops and the fossils and the new routes forming in real time, points toward the same quiet truth. Migration is not a behavior that birds perform. It is something closer to what birds are. It is woven into their physiology, their neurology, their genes, their sense of time and light and magnetic direction. It is the accumulated answer to a question the seasons have been asking for millions of years. Where should you be? And when? And how will you get there? The birds have been answering that question longer than we have been asking it. And yet the question of cost is worth sitting with for a moment. Because migration is not easy. It has never been easy. The energy alone is staggering. Weeks of accumulated fat burned down to almost nothing over the course of a single crossing. Then there is the predation, the storms, the disorientation over featureless water, far from any landmark, and darkness. A bird that sets out may not arrive. Many do not. And still, across the long history of birds, migration has evolved again and again. Not once, not in a single ancestral lineage that passed the habit down to all its descendants, but independently in lineages that share no recent common ancestor. Shorebirds and warblers and raptors and swifts and hummingbirds, each arriving at the same solution through their own separate path. The benefits, measured across millions of generations, kept winning. That is worth holding quietly, not as a triumph, but as a kind of arithmetic written in survival. The costs were real, and the benefits were real, and the benefits were larger. That is all. That is everything. Not every bird within a migratory species makes the journey, though. In many species, only part of the population migrates at all. Some individuals stay, some go. They may be the same species, nesting in the same woodland, and yet in autumn, their paths diverge. One bird lifting into the sky, another settling deeper into the familiar trees. This pattern is called partial migration. It is more common than most people realize, and it sits in an interesting place. Evolutionarily speaking, It may represent a population in transition, moving toward full migration, or perhaps away from it. The balance between staying and going, not yet fully resolved. The environment shifts, the costs and benefits shift with it, and the population follows slowly, over generations. Within partially migratory species, the split is sometimes not random. In some, it falls along lines of sex. Females migrate while males remain, or males migrate while females stay. The reasons vary, but one recurring explanation is competition. If the two sexes winter in different places, they are not competing with each other for the same limited food. The resources stretch further. Both survive better than they would if they crowded into the same patch of winter habitat. Raptors show this pattern clearly. In some hawk and falcon species, females winter farther north than males. The females, being larger, can handle colder conditions and dominate the better northern territories. The smaller males travel farther south, where competition is lower and the climate more forgiving. Two strategies, shaped by the same pressure, diverging quietly along the axis of size. All of this movement, whether a short shift or an ocean crossing, runs on fat. Fat is the fuel of migration, almost exclusively. It yields more than twice the energy per gram that protein does. A bird that has spent weeks accumulating fat reserves carries within its body a dense, efficient store of energy that can sustain flight for days. The fat is deposited beneath the skin, around the organs, in layers that give pre-migratory birds a softness, a roundness that disappears entirely by the time they arrive. When the fat runs low, toward the end of a very long flight, when the reserves are nearly gone, some birds begin to draw on something else: muscle protein. The body begins to catabolize its own tissue, breaking down muscle to extract the energy needed to keep flying. It is a measure of last resort, and it is costly. Muscle loss during a crossing must be rebuilt at the next stopover, which takes time and food. But not all muscle is treated equally. The heart and the flight muscles are largely spared, even as other tissues are broken down. The body protects what it cannot afford to lose. A bird that loses its flight muscles mid-ocean does not arrive, so the catabolism works around them, carefully, preserving the machinery of flight even as it consumes everything else. The rates at which migratory birds process fat during flight would, in a sedentary mammal, signal something gone wrong. The metabolic machinery is running at a pace that would be considered pathological in a creature not built for it. But migratory birds are built for it. Their physiology has been shaped over millions of years to sustain exactly this kind of extraordinary expenditure without damage. Much of this begins in the liver. The liver is the quiet center of the pre-migration transformation. In the weeks before departure, it works at an elevated pace, converting the carbohydrates and proteins from the bird's diet into fatty acids, the building blocks of the fat stores that will fuel the journey. During this period, the livers of migratory birds are often measurably enlarged, swollen with the work of conversion. The bird eats, and the liver transforms, and the fat accumulates, and the body grows heavier and rounder and more ready. Then the bird departs, and the liver's role shifts. Now it helps manage the mobilization of those stores, releasing fatty acids into the bloodstream as the muscles demand them, hour after hour, through the long hours of the night crossing. At stopovers, the digestive system takes over with its own kind of urgency. Some migrants can absorb nutrients at rates that seem almost implausible for their size. A thrush resting in a coastal thicket, feeding on berries, can double its fat stores in as little as 3 days if the food is good and the conditions are calm. The gut expands to meet the demand. Enzymes increase. The whole digestive apparatus accelerates, as if the body knows exactly how much time it has and exactly how much it needs to accomplish. This is the rhythm of migration at the physiological level, not a single sustained effort, but a series of transformations: fattening, flying, depleting, resting, fattening again. The body is never quite the same from one stage to the next. It grows and shrinks and grows again, reshaping itself around the demands of the journey. And somewhere inside all of this, inside the liver working through the night, inside the fat reserve slowly burning, inside the muscle held carefully in reserve, there is still the navigation, still the magnetic field threading through the retina, still the stars turning overhead, still the inherited direction, the ancient vector pointing the way. A small bird, weighing less than a handful of seeds, crossing a dark ocean, its body a carefully managed fire of fat and muscle and chemistry, and somewhere in its brain, a map it did not draw, pointing toward a place it has never been. That is what is happening tonight above us, quietly. And so the bird lands. After hours or days above open water, above cloud and darkness, it finds a tree, a reed bed, a hedgerow at the edge of a field, and it stops. The body, which has been burning steadily through its reserves, now shifts into a different mode entirely. The urgency of flight gives way to something quieter, the slow, patient work of rebuilding. A thrush, for instance, arriving at a good stopover site in autumn can double its fat stores in as little as 3 days. 3 days of feeding well, resting in cover, sleeping when it can. And the body fills again, layer by layer, ready for the next crossing. But not every stopover is equal. The quality of the habitat matters enormously. A site with abundant food, ripe berries, dense insect populations, soft ground full of earthworms, allows a bird to refuel quickly and move on. A degraded site, stripped of its resources, forces the bird to linger longer, burning time it does not have. And time, in migration, is not abstract. It is breeding success. It is survival. Birds that refuel quickly and arrive at their destinations earlier tend to claim better territories, find better mates, begin nesting while conditions are still favorable. The days saved at a single stopover can ripple forward through the entire season. A few extra hours of feeding in a coastal thicket in October may translate, months later, into a nest that succeeds rather than one that fails. This is why the loss of stopover habitat is so consequential. It is not simply that a patch of woodland disappears. It is that a link in a chain is weakened, and the chain runs all the way from one continent to another. But there is another pressure at stopovers, one that has nothing to do with food. Predators know about migration too. Hawks and falcons have learned, over their own long evolutionary history, that migration corridors are places of abundance. A sparrowhawk perched at the edge of a coastal wood in autumn is not there by accident. It is waiting for exactly what arrives. Small birds, tired, focused on feeding, their attention divided between hunger and fear. The migrating bird must balance these two demands constantly. Feed too boldly, and a falcon takes it from the open. Feed too cautiously, and the fat reserves never rebuild. Every moment at a stopover is a negotiation between the need to eat and the need to survive long enough to eat again. One response to this pressure is to gather. Migrating birds often feed in dense flocks, and the logic is straightforward. Many eyes see more than one. When dozens of birds are feeding together, the chance that at least one will notice an approaching hawk is much higher than if a single bird feeds alone. The individual bird can spend more time with its head down, searching for food because its neighbors are watching. And the flocks that form at stopovers are often not composed of a single species. Thrushes and warblers, finches and pipits may feed together in loose mixed assemblies. Different species have different alert behaviors, different vantage points, different sensory strengths. Together, they form a kind of distributed vigilance network, each species contributing something the others lack. There is a quiet cooperation in this, though cooperation may be too strong a word. Each bird is acting in its own interest, and yet the effect is shared. Not all predators wait at stopovers. Some follow the migration itself. The peregrine falcon is among the fastest animals on Earth, and it has learned that migration corridors offer a reliable, concentrated food supply. Peregrines have been observed moving along coastlines and ridgelines during autumn, hunting the stream of passing birds. They do not need to wait in one place. The migration comes to them. And then there is Eleonora's falcon. This is a bird that has arranged its entire breeding calendar around the autumn migration of small birds. Eleonora's falcons nest on rocky Mediterranean islands, the Canary Islands, the Balearics Islands off the coast of Greece and Morocco, and they breed late, in summer, timing the hatching of their chicks to coincide precisely with the peak of southbound migration. When the chicks are hungriest, the sky above the Mediterranean is full of small birds crossing from Europe toward Africa. The falcons hunt them in the air, carrying them back to the nest still living, storing them briefly in rock crevices. The migration of one species becomes the food supply of another. It is a precise and ancient arrangement. The falcon's breeding season is, in a sense, a clock set to the migration calendar of birds it has never met. But predators are not the only hazard that concentrates at stopovers. Parasites do too. Crowded conditions, many birds of many species, resting in the same thickets, drinking from the same pools, create opportunities for the transmission of lice, mites, blood parasites, and pathogens. A bird that arrives healthy may depart carrying something it did not have before. Some migratory species appear to respond to this. Their immune function rises during migration, as if the body anticipates the increased exposure to novel organisms. The defenses are elevated before the threat fully arrives. But this comes at a cost. The immune system is not free to run. It requires energy, protein, cellular resources. And during migration, all of those things are already spoken for. The flight muscles need fuel. The fat reserves need to be maintained. The brain needs to navigate. The immune system must compete for the same limited budget. There is a tension here that the body manages imperfectly. Mounting a strong immune response during a long flight may not be possible. The bird may arrive at its destination more vulnerable than it left, or it may suppress the immune response during the crossing and pay the cost later. Exactly how this balance is struck varies by species, by individual, by the severity of the journey. It is one of the quieter physiological dramas of migration, largely invisible from the outside. And there is one more dimension to this. Migratory birds move across vast distances, crossing between ecosystems that have evolved in partial isolation from one another. A bird that picks up a pathogen on its wintering grounds in West Africa may carry it to a breeding site in Scandinavia. A bird infected in the wetlands of East Asia may carry that infection along the flyway to Australia. This is not a flaw in migration. It is simply what movement does. It connects places that would otherwise be separate. It carries things, seeds, parasites, nutrients, pathogens, across distances that nothing else would cross. The role of migratory birds in the spread of diseases like avian influenza is real, and researchers study it carefully. But the picture is not simple. The birds are not merely vectors. They are also subject to the diseases they carry. They fall ill. They die. They recover. They are participants in the ecology of infection, not just its messengers. Migration is, among other things, a vast mixing event, a reshuffling of the biological world, twice a year, along routes that have been traveled for millions of years. And the birds that survive it, the ones that refuel in time, evade the falcon, carry their parasites lightly, navigate the crossing, arrive at the other end changed. Lighter, leaner, carrying within them the chemical record of every place they have been. And they rest. And they rest. As the bird rests, the atmosphere above continues its slow work. Wind moves in layers. At different altitudes, it flows in different directions, at different speeds. And migrating birds, as far as we can tell, are not indifferent to this. They choose. The altitude a bird flies at during migration is not simply a matter of how high it can go. It is, in many cases, a matter of where the wind is most useful. Some species climb to altitudes where tailwinds are strongest, even when that means flying in air that is colder, thinner and darker. The energy saved by riding a favorable wind can be the difference between arriving with reserves intact and arriving depleted. This is a kind of meteorological intelligence, not conscious, perhaps, but real. Before a bird departs on a migration night, something in it is reading the sky. Wind direction, temperature, the slow rise or fall of barometric pressure, these all appear to influence the decision. On nights when the wind is wrong, many birds simply wait. They remain in the reeds, in the hedgerows, in the coastal scrub, feeding if they can, resting, holding the journey inside them like a question not yet answered. And then the pressure shifts. The wind turns favorable, and they go. Thousands of them, sometimes tens of thousands, rising from the landscape in the last light of evening and climbing into the dark. But the weather does not always cooperate. Sometimes a bird is already over the sea, already committed to a crossing, when the wind turns against it. A headwind builds. Rain begins. The air that was carrying the bird forward now pushes back, and the bird, burning fuel it cannot replace until it lands, must make a choice. It descends. This is what birdwatchers call a fallout. When migrants are forced down by storms or headwinds, they concentrate in the first land they reach: coastal headlands, small islands, the narrow strips of trees at the edge of a cliff. Birds that would normally pass invisibly overhead, high and fast and gone, suddenly appear in numbers, exhausted, hungry, sitting in the open in ways they would never do if they had a choice. Fallouts are, in one sense, a record of difficulty. Each bird that lands in a coastal thicket after a hard crossing has survived something. It has crossed water on failing reserves and found ground beneath it in time. Birdwatchers travel long distances to witness these events, and what draws them is not only the spectacle, it is the chance to see species that would otherwise never appear in that place. Birds blown far outside their normal range by the same winds that grounded them. A warbler from Siberia in a British garden. A thrush from North America on an Irish headland. The storm that exhausted the bird also carried it somewhere new. There is something quietly remarkable in that. Most of what a migratory bird knows about its route, it was born knowing. The direction, the distance, the rough shape of the journey. These are encoded in the genome, passed from parent to offspring, without a single lesson being taught. A young bird on its first migration has never seen its wintering grounds. It has never flown the route before, and yet it goes, and it arrives, guided by inherited instructions it cannot read, but cannot ignore. The social transmission of route knowledge is limited compared to this deep genetic inheritance, but it is not absent. Young birds that migrate in flocks alongside experienced adults may absorb something from the journey, not the whole route that is already inside them, but the details, the specific bend in a river where food is reliable, the sheltered bay where the wind drops and the water is calm, the particular stand of trees where a stopover is safe. In some species, family groups migrate together, parents and young, moving as a unit through the landscape. And in these cases, the young birds may be learning something that cannot be inherited, something that must be shown. This distinction matters more than it might seem. For most small songbirds, the family disperses before migration begins. Each bird travels alone, guided entirely by what it was born with. But for larger, longer-lived birds, birds whose routes are more complex, whose stopovers are more specific, the transmission of knowledge across generations may be essential. And when that transmission breaks, the whooping crane is one of the tallest birds in North America, white, with a red crown, a wingspan of more than 2 meters, and by the middle of the 20th century, there were fewer than 24 left in the wild. The population had collapsed so completely that the traditional migration routes, the specific corridors, the specific stopover wetlands, the specific wintering grounds had been lost. There were simply not enough birds left to carry the knowledge forward. Recovery programs brought the population back from the edge. Eggs were hatched in captivity. Chicks were raised carefully. But a crane raised in an enclosure, however well cared for, does not know where to go. And so researchers tried something that had never been done before. They used ultralight aircraft, small, slow, open-framed machines to lead the cranes south. The aircraft flew ahead, and the cranes followed. The pilots wore white costumes and avoided speaking, so the birds would not imprint on a human figure, but on the aircraft itself, which moved through the air the way a large bird moves. A surrogate parent, made of aluminum and fabric, leading a column of white cranes across the sky. The cranes followed. They followed the aircraft from Wisconsin to Florida, learning the route as they flew it, crossing rivers, skirting cities, descending into the same wetlands each evening. And the following spring, some of them flew the route back north on their own, without the aircraft, without the pilots, carrying within them a route that had been shown to them, not inherited. This was not a small thing. It demonstrated, quietly but clearly, that at least some of what large migratory birds know about their roots is not written in their genes. It is cultural. It is transmitted. It can be lost when the chain of transmission breaks, and it can, with great care, be restored. The Whooping Crane Project is ongoing. The population is still small, still fragile, but the cranes are flying routes that did not exist a generation ago, routes that were built by a collaboration between birds and the people trying to save them. There is something in that worth sitting with. A bird that inherits its route from its genome is following a map written by millions of years of selection. A bird that learns its route from a parent is following a map written by experience, passed forward through time. And a crane that learned its route from an ultralight aircraft is following a map that was, in a sense, given back to it, a route reconstructed from what was almost lost. All three of these are real. All three are happening, somewhere, tonight. In the dark above the continent, birds are climbing to find the wind, waiting for the pressure to shift, crossing water they cannot see the end of, resting in coastal thickets after crossings that nearly didn't happen, flying in loose formation with parents who know where the good water is. And somewhere, a small flock of white cranes is moving south along a corridor that was taught to them by something that flew ahead. The sky holds all of this at once. And the sky holds something else, too. Something that shifts beneath all of it, slowly, the way continents shift. The magnetic field of the Earth is not fixed. It moves. Over decades, over centuries, the field drifts, the poles wandering, the lines of inclination tilting by fractions of a degree, year by year. This is not something a single bird would notice in a single lifetime. But over generations, the field that birds have been reading for millions of years is quietly rewriting itself. Some researchers have wondered whether long-term changes in migration routes, the gradual bending of ancient corridors, the slow drift of wintering grounds, may partly reflect this. That the routes themselves are tracking the field, following it the way a compass needle follows north, not in a single moment, but across deep time. It is a difficult thing to test, but the idea has a certain quiet logic to it. A map that is itself in motion, and the creatures that read it, moving with it, generation by generation. Without ever knowing, the map has changed. What we do know is that the magnetic poles are currently moving faster than they have in recorded history. The North Magnetic Pole has been drifting towards Siberia at an accelerating rate. Whether this will eventually affect the birds that rely on magnetic inclination to find their way, no one can say with certainty. The field has always moved, and birds have always found their way. But the pace of change is something researchers are watching, quietly, with attention. What makes the system resilient, as far as we can tell, is that no bird relies on a single compass. The magnetic field is one layer, but birds appear to recalibrate it constantly, checking it against the sun, checking it against the stars. On a clear morning, the sun compass and the magnetic compass are compared, and any drift is corrected. On a clear night, the stellar compass and the magnetic compass are aligned again. The three systems are not independent instruments pointing in different directions. They are in conversation with each other, each one checking the others, each one being checked. This cross-calibration is what makes the whole system more robust than any single mechanism could be on its own. If the magnetic field shifts slightly in a region of unusual geology, the sun compass can correct for it. If clouds obscure the stars for several nights, the magnetic compass holds the heading. If the sun is hidden and the stars are hidden, and the night is fully overcast, which it sometimes is, over the ocean, in autumn, the bird flies on the magnetic field alone. And it is enough. Not perfect, but enough. There are places on Earth where the magnetic field is locally distorted, where ancient volcanic rock or dense deposits of iron-bearing minerals bends the field lines away from their expected angle. In these regions of magnetic anomaly, some birds show signs of disorientation, brief confusion, a hesitation in the heading. The Bermuda Triangle, that stretch of the Western Atlantic that has gathered so much human mythology, does overlap with a region of magnetic anomaly. But as far as researchers have been able to determine, this has no measurable effect on bird migration. Birds cross that water every autumn, in their millions, and arrive where they intended to arrive. The anomaly is real. The effect on birds, if any, is too small to detect. Which is perhaps a reminder that the navigation system, with all its redundancy, is more capable than any single disturbance can easily overcome. And then there's something else entirely, something that operates below the threshold of human perception. Infrasound. Sounds so low in frequency that no human ear can register it. Vibrations in the range of 1 or 2 cycles per second, or even slower. These sounds travel enormous distances without losing their shape. Mountain ranges generate them as wind moves across ridges and through valleys. Coastlines generate them as ocean waves compress the air against the shore. River valleys carry them, channeling low vibrations along their length like a slow current. Each landscape has its own infrasound signature, a kind of acoustic fingerprint, inaudible to us, but potentially readable to a bird in flight. The hypothesis is still being explored. But some researchers believe that migratory birds may use infrasound as a form of landmark recognition, not seeing the mountains below, but hearing them in frequencies that pass through cloud and darkness without difficulty. A bird crossing the Appalachians on an overcast night might not see the ridgeline, but it might feel the ridgeline as a pattern of pressure in the air, a familiar vibration that says, "Here is where the land rises. Here is where you are." If this is true, and the evidence is suggestive rather than conclusive, then the sensory world of a migrating bird is richer than we have imagined. Not just visual, not just magnetic, but acoustic in frequencies we cannot share. The full picture, as best we can assemble it, is of a bird that integrates information from many channels at once. The angle of the sun, filtered through an internal clock. The rotation of the stars, learned in a sensitive period before the first migration ever began. The inclination of magnetic field lines, read through a light-dependent reaction in the retina. The infrasound of the landscape below. The smell of the wind, carrying the chemical signature of distant places. All of this arriving simultaneously, being weighted and combined, producing a heading, a direction, a sense of where to go. We do not fully understand how the brain accomplishes this, but we know something about where it happens. The hippocampus, a region of the brain involved in spatial memory and navigation, is enlarged in migratory species compared to closely related non-migratory ones. Birds that must hold complex maps in their minds have more hippocampal tissue to hold them with. And the hippocampus does not stay the same size throughout the year. Before migration, it grows, the tissue expands, new connections form, the capacity for spatial processing increases. And afterward, when the journey is complete and the bird has settled into its wintering grounds, the hippocampus shrinks back. The brain builds itself up for the crossing, then releases what it no longer needs. This is neuroplasticity in one of its most visible forms. The brain remodeling itself with the seasons, the way a tree puts out leaves and then draws the resources back. There is something very quiet in that image. A small bird, somewhere in the dark above the Atlantic, carrying within its skull a brain that has grown specifically for this moment, enlarged for the crossing, holding the map. And when the crossing is done, when the bird has landed in the warmth of its wintering ground and the urgency has passed, the brain will gently let it go. Until spring, when the days lengthen again and the field lines tilt in their familiar way, and the stars wheel overhead at the pattern learned long ago. And the hippocampus begins, quietly, to grow again. The night before a bird departs, something shifts in the brain. Not dramatically, not all at once, but in the regions associated with spatial processing, the areas that hold maps, that track position, that orient the body in space. Activity rises quietly through the hours of darkness. The bird is not yet flying. It is still perched, still breathing slowly in the dark. And yet its brain is already, in some sense, preparing the crossing. This is one of the more recent observations in migration research, and it connects to something that may seem surprising at first: sleep. Sleep itself may be part of the preparation. There is a hypothesis, still being explored, that the stellar compass, the bird's ability to orient by the rotation of the night sky, is not simply used during migration, but is actively calibrated during sleep. That as the bird rests, the brain is processing the day's observations, refining its model of the sky, adjusting the internal map. This would mean that sleep is not a pause in navigation. It is part of navigation. The connection between sleep, memory consolidation, and the migratory state is an emerging area of research. The details are not yet settled, but the possibility is there, quiet and remarkable, that a bird sleeping in a hedgerow before its first great crossing is, in some sense, already learning the route, already reading the stars with its eyes closed. And when it lifts into the air the following night, guided by the wheel of constellations overhead and the faint inclination of the magnetic field beneath its wings, it carries something that is difficult to name precisely. It is not knowledge the way we usually mean the word. It was not taught. It was not written down. It was not passed from parent to child in any language. It is older than language. A migrating bird crossing an ocean at night carries within it a kind of knowledge that predates human thought by millions of years. The routes it follows, the cues it reads, the timing it obeys. All of this was shaped long before there were words for any of it. Long before there were words at all. The routes taken by migratory birds today were not invented recently. They were carved, slowly, by forces that operated across geological time. Ice ages, continental drift, millions of years of natural selection favoring the birds that found food, that survived the crossing, that returned in spring to breed. The migrations we observe now are the accumulated result of all of that. Every route is a kind of fossil, preserving the memory of ancient climates and ancient landscapes. Roughly 12,000 years ago, the last great ice sheets began to retreat. The glaciers pulled back from the northern continents, and behind them, slowly, came the land. Tundra first, then shrub, then forest. And behind the expanding habitat, following the warmth northward, came the birds. The long migrations of today may have begun as much shorter movements. A bird that once traveled a few hundred kilometers to reach its breeding ground found, over generations, that the breeding ground had moved farther north, and the migration stretched with it, lengthening over thousands of years, following the ice as it withdrew, until some species were crossing entire oceans to reach the places where their ancestors had once simply flown to the next valley. The Arctic turns 70,000 kilometers, The godwit's 11-day crossing of the Pacific. These may be the extended echoes of journeys that were once far more modest, stretched by time, stretched by ice. And we can sometimes read those ancient journeys in the birds themselves, even in birds that are no longer living. Fossils of migratory birds are rare. The bones of small birds are fragile, and the conditions required to preserve them are uncommon. But there is another way to look into the past. Feathers. A feather, while it is growing, records the chemistry of everything the bird consumed. The food, the water, the soil those things came from. All of it leaves a trace in the structure of the feather, in the ratios of stable isotopes locked into the keratin as it forms. Different regions of the Earth have different isotopic signatures. The water in one river valley is chemically distinct from the water in another, in ways that are subtle but measurable. And those differences are absorbed by the plants, and by the insects that eat the plants, and by the birds that eat the insects. So a feather carries, written in its chemistry, a record of where it grew. By comparing the isotope ratios in a feather to maps of isotope variation across the landscape, researchers can estimate where a bird was when that feather formed, where it was molting, where it was spending its time. This technique has been used to reconstruct the wintering grounds of species that are poorly known, or that were never directly observed on their wintering grounds. And in some cases, it has been applied to museum specimens, feathers collected decades or centuries ago, preserved in drawers, holding within them a chemical memory of places the bird visited long before anyone thought to ask. Even the feathers of extinct species can sometimes be read this way. A bird that vanished before modern tracking technology existed, leaving behind only a handful of preserved specimens, may still carry in its feathers the faint signature of a landscape it once knew. The past is not entirely silent. It speaks in isotopes. And all of this, the isotopes, the feathers, the fossils, the radar screens, the geolocators, the cryptochrome molecules in the retina, the hippocampus that grows and shrinks with the seasons, all of it belongs to a field of study that has grown to touch nearly every branch of biology. Genetics, because the migratory program is inherited, encoded somewhere in the genome, passed from parent to offspring across generations. Neuroscience, because the brain is actively remodeling itself to support the crossing, building new connections, expanding the regions that hold the map. Ecology, because migration connects distant ecosystems, moving nutrients and energy across continents, linking the Arctic tundra to the African savanna, the Alaskan coast to the wetlands of New Zealand. Physiology, because the body of a migrating bird is doing things that push against the limits of what living tissue can sustain, burning fat at extraordinary rates, shrinking organs, rerouting blood, sleeping with half a brain. And evolution, because migration itself is a product of deep time, shaped by selection pressures that operated across millions of years, preserved in routes that are older than the landscapes they cross. It touches physics through the quantum biology of cryptochrome. It touches meteorology through the study of wind-assisted flight and the pressure systems that ground 1,000 birds in a single night. Migration is, in a sense, a conversation between a small living body and the entire planet. Its fields, its winds, its light. A small bird, weighing less than a handful of seeds, lifts off from a shoreline in the dark. Below it, the land falls away. Ahead, there is only ocean. The stars wheel slowly overhead in the pattern the bird learned before its first migration, watching the sky rotate around the still point at the pole. The magnetic field lines tilt at their familiar angle beneath its wings, and somewhere inside its skull, in a hippocampus that has grown specifically for this moment, a map is being held. Not a map drawn on paper. Not a map that can be described in words. A map older than words, carried quietly across the dark water. And that map is being carried right now. Somewhere over dark water, a small bird is flying. It has no name for what it is doing, no concept of distance, or courage, or the vastness of the ocean beneath it. It simply flies, drawn forward by something older than thought. And it has been this way for a very long time. Every spring, across every human culture that has ever lived close to the land, the return of migratory birds marked something, a threshold, the moment when the cold began to release its hold, when the first swallows appeared over a field, or the first cranes called from somewhere high and invisible in the sky. People understood that the growing season had come again. They did not know where the birds had been. They only knew they had returned. And for a long time, that was enough. The mystery of where birds went in winter was one that early thinkers tried to answer with the tools they had. Aristotle, who observed the natural world with great care and genuine curiosity, believed that swallows disappeared each autumn into the mud at the bottom of ponds, that they sank down into the cold silt and waited there, suspended until warmth returned. It was not an unreasonable idea for its time. Swallows vanished suddenly, and ponds were nearby, and the world was full of things that slept through winter. This idea persisted. For roughly 2,000 years, the hibernation hypothesis moved quietly through European natural history. Scholars repeated it. Fishermen claimed to have pulled sleeping swallows from beneath the ice. The idea had a kind of logic to it, and so it endured. It was not disproved until the 18th century, when patient, systematic observation finally made the old explanation impossible to hold. But the clearest proof of all came not from observation, but from accident. In 1822, a white stork was found in the region of Mecklenburg, in what is now northern Germany. The bird was alive, and through its neck, lodged there, and somehow survived, was a spear. Not a European spear, an African one, carved from a wood that did not grow anywhere in Europe. The stork had been struck somewhere in sub-Saharan Africa. It had carried the spear with it, across the Mediterranean, across the continent, all the way back to its breeding grounds in Germany. This bird became known as the Fielstorch, the arrow stork. It demonstrated, in a way no argument could, that European storks wintered in Africa, that the distance between a German meadow and the African interior was not a barrier, but a route. The storks had been flying, quietly, for longer than anyone had thought to ask. The word migration comes from the Latin migrare, simply meaning to move from one place to another, a plain word for something that turns out to be extraordinarily deep. After the Fielstorch, the science of migration began to take shape, and one of its most important tools was also one of its simplest. A small metal band attached to a bird's leg, stamped with a number. Bird ringing began in the early years of the 20th century. The idea was straightforward. Mark a bird, release it, and hope that somewhere, someday, someone would find it again and report the number. Over time, millions of birds were ringed, and the recoveries accumulated. A warbler ringed in Britain, found in West Africa, a godwit banded in Alaska, recovered in New Zealand. Each recovery a single thread, and together they wove a picture of routes that had been invisible before. Countless migration paths were mapped this way, through patience and chance, and the willingness of people all over the world to look carefully at the leg of a bird they had found. Among all the birds ever ringed, one has become something of a quiet legend, a Laysan albatross, banded in the middle of the 20th century on a small island in the Pacific. She was given the name Wisdom. Wisdom is still alive, still breeding. At an age of more than 70 years, she continues to return each season to the same island, to the same nesting ground. She has outlived the researchers who first banded her. She has raised chick after chick across decades that saw the world change in ways no one in 1956 could have predicted. Over her lifetime, she has flown an estimated 5 million kilometers. 5 million? That number is almost too large to hold, but it belongs to a single bird, with hollow bones and a heart the size of a walnut, navigating by wind and wave, and some internal knowledge of the Pacific that she has carried and refined across 7 decades of flight. She is still out there, somewhere, right now. The study of migration continues to yield things that were not expected. New tracking technologies, satellites, miniaturized geolocators, radar networks spanning entire continents, keep revealing routes and behaviors that no one had observed before. Species found to take entirely different paths in spring and autumn, birds crossing barriers that were thought to be impassable, individuals making journeys whose length, when finally measured, seemed almost implausible. Each new discovery quietly expands what we understand to be possible for a small living body moving through the world. And yet, the essential image remains the same as it has always been. A bird, small enough to hold in one hand, lifting off from a shoreline in the dark, crossing water that has no other shore visible. Guided by the tilt of magnetic field lines it may perceive as something like light. By the rotation of stars it learned to read before it had ever flown. By a direction and a duration encoded somewhere in its cells before it hatched. Carrying no map that can be unfolded, no instrument that can be named, only the accumulated inheritance of millions of years, held quietly in a body weighing less than a handful of seeds. This is one of the quietest wonders the natural world contains. Not loud, not dramatic. Happening mostly in darkness, mostly unseen, mostly in silence. 50 billion birds, moving across the face of the earth each autumn. And each one of them carrying something ancient. Something that has crossed every ice age, every shifting coastline, every slow rearrangement of the continents. Still intact, still working. A small bird over dark water. The stars turning slowly overhead. The field lines tilting at their familiar angle. And somewhere far ahead, a place it has never been, that it is already going home to.